Hello all. So, in this lecture, we are talking about the number theory. So, the number theory in essential means the study of the numbers. So, it is quite basic because the first journey of our mathematics starts with the numbers. Okay. So, what you can see that whenever we started our journey in mathematics back in our pre-nursery classes, that is in our kindergarten classes, we started by counting 1 2 3 4 and all the way up to 100, maybe 200 and so on. And similarly, all of our these studies are just revolting around the numbers. So in later cases, when we see the integration, the differentiation, or maybe the geometry and everything in mathematics is related to a number. Not only mathematics, but also when we talk about some physics, maybe some biology, maybe some chemistry, in different aspects we see just numbers, right? Whenever we just talk about some forces, that is a fundamental if we are talking about a fundamental force that has a number like 3 newton or maybe 4 newton or maybe 10 to the power minus 34 newton and so on. And similarly, when we talk in chemistry, we see that 1 mole is equal to 6.022 into 10 to the power 23. That is a number. So everything in our world is wrapped with numbers. We perceive things in terms of numbers. Whenever you watch a football match, you count how many goals is being scored. You count them. Similarly, when you watch a cricket match, maybe you just watch what is the run, what is run rate, what are the over what is the run rate, maybe I said that, and which over is it now playing on and something like that, and each and everything is talking about numbers. So we start our journey to this number theory uh, via certain tools. I am not talking about those tools because those are quite fundamental. So for the sake of completion, let me mention them first. Okay, the script is a bit thick. Let me just scale it down a bit. Yeah, here it is. Go. So first, we know about the factorizations. Factorization means how many divisors are there when you are given a number. That means how many numbers are there that can divide a given number. There is factorization. There is principle of mathematical induction, and this is quite fascinating thing. So in logic there are two types of truth. There is bigger truth and the smaller truth. Bigger truth means the universal truth, that is true, that holds true for each and every being in this universe. And there are some individual truths, that is small truths, that is only holding, that is hold for small individuals or maybe small groups or maybe something like that. So if I say Mr. X is a person and his height is 5 feet 11 inches, so that is a true statement, but that only holds for Mr. X. We cannot just generalize it to the whole universe that all men, all persons are 5 foot 11 inches. That is not true. Similarly, man is mortal. That is something called the bigger truth or the universal truth. That means whenever you take a man, you can just tell that he is a man. Okay, all men are immortal. Uh, so Mr. X is a man, so he is also mortal. That is called the smaller truth. and the universal truth. The universal truth that holds for each and every being on this universe, and the individual truth just holds for certain individuals or certain groups. So when we conclude a universal truth starting from an individual truth, we call it as induction, and when we do the other way around, we call it a deduction. So you can see that old Sherlock Holmes movies or say stories, he always uses the term deduction. That means he always look like every Chinese person have a tattoo of fish in their hand, and therefore he has a tattoo of fish in his hand, so he is a Chinese. Something like that type of arguments you can always find in case of the Sherlock Holmes stories. So that is a classical example of deduction. But there is also there is also a notion of induction, and if that induction is strictly bounded to some mathematical property like division, like some other notions like number of a form, mm, certain form like 3n plus 1 or 2n plus 1, a number is 2n plus 1, and a number is odd, a number is even, something which is restricted to very mathematical notions, we call it the principle of mathematical induction. Then there comes something called the fundamental theorem of arithmetic. Well, this is also very fundamental, as we can perceive from the name itself that it is a fundamental theorem of arithmetic. That must be very fundamental, and it is very trivial actually if you look very closely. Since our childhood, we all know how to write a number as a product of primes. Like if you are given like 7, then we can write it as like 7. If you are given 3, you can write it as like 3. But if you are given like a 12, you can write it as 2 into 2 into 3. That is a product of some prime numbers. If you are given 10, you can write it as 2 into 5. So each and every numbers, you can just it must be an integer obviously, so that can be written as a product of some primes, and that is unique up to the arrangements. That is, up to the arrangement means you can write 2 into 5 and 5 into 2. And if you think like that, it is unique, that it cannot be a multiplication of two numbers, say p1 into p2, such that p1 and p2 does not belong to this set. You cannot write like that. So in essence, that means that up to arrangement, this factorization is always unique, and this is known as the canonical factorization of a number. And the general convenience, the convention is actually to write it like the smaller number first, then the bigger number, and so on. Okay, so this gives me some very good idea of factors. Then there comes GCD, the greatest common divisor. You all know these things from your preschools. Maybe the first grade or second grade, you have all figured it out, how to find GCD, how to write a number in canonical factorization. So I will not waste my time on these very topics, but well, these are all certain properties of integers. So the number theory, in some elementary sense, generally deals with the natural numbers and the integers. So we start our journey from a very known and a very trivial yet important result called the division algorithm. The division algorithm is something quite fascinating, but it is very trivial, as you can see. Let me write the division algorithm. Um, Given A and B be two integers, then there exist unique Q and R such that A is equal to sorry, just hold on a minute. B is equal to AQ plus R, and what are the other conditions? That R is something specific, that R is greater than or equal to 0 and obviously less than B. That is important. You can see that the remainder is always less than B, and what you can say, that it may be 0 and it is always greater, or it can be always greater than 0, but nonetheless it will be always less than B. So some notations: this is known as the dividend, this is known as the quotient, this is known as the divisor, and this is my remainder. So you can take any number, may it be 10, 2, may it be 5, 4, it may be any numbers, any integers. You can always find such a thing. So after this division algorithm, we will discuss certain things that is quite fascinating actually. After this division algorithm, we discuss certain well ordering principle. Okay, let me write that down. Well ordering principle. So from the name you can just guess that what does it say, the well ordering. So that means there is a principle that states us that something is well ordered. So what is well ordered? So here is the answer. Take any finite subset, or maybe you may not take any finite subset, but well, fine, any subset, you can take any subset of the natural number system. What can you say about this natural, the subset? That there exists an A in A such that A is less than or equal to X for all X in A. That means you can, if you take a subset of natural numbers, that means what is natural number? For our discussions, the natural number will be 1, 2, 3, 4, and all the way up to infinite. There is some concept of whole numbers that will just incorporate natural numbers union 0. Then there comes Z, that means natural number union the 0 union the negatives of the natural numbers. That is my Z. So we will restrict our whole discussion all the way up to Z only. So now you can check that whenever you will take any subset of N, the well ordering principle says any subset you can take, there will be an element in that subset of N, that is A, there will be an A in A such that no matter which member you pick from the subset A, that will be obviously either equal or greater than A. As for example, say n is n and a be this set, 1, sorry, not 1, maybe 10, 30, 13, 6. So this is my subset of n. So you can always find an element 6 such that all other elements from A is obviously greater than or equal to 6. You can see 10 is greater than 6, 30 is greater than 6, 13 is greater than 6, and 6 is equal to 6. Okay. So this is called well ordering principle. Now we will go to some very fascinating area called the congruences. Well, the congruence means a bit philosophical way. Congruence means similarity. So we will see that what similarity you can check actually. So from here we can recall the division algorithm, and then we are hoping to understand the congruence. Well, there is a notion of remaindering. Well, we can always remainder things in our daily life every now and then. As for example, suppose it is 9:45 and you have to leave within next 30 minutes. So what will you say? That you will leave at 9:75? Suppose the time is 9:45 a.m. and you have to leave within 30 minutes. So what will you say? You will say that you will leave at 9:75? No, right? You will say that I will leave at 10:15 a.m. Why? How are you telling that 9:45 plus 30 is equal to actually 10:15? We are actually taking this 45 minutes plus 30 minutes, that is 75 minutes, and then using division algorithm we are doing 75, we are quotienting it by 6. So I will get one quotient and one remainder, and that remainder will give you that it will be 15 minutes. But how much? It already having quotient 1, that means the hour will be raised by 1. So the whole thing will be 10 and 15, that will be 10:15 am. I hope this is clear. So suppose we are talking about a world where everyone knows how to calculate only up to 12, or maybe let us talk about the very ancient times when there were only fingers, that is uh, f- uh, the forefinger, the index finger, the middle finger, and the ring finger, and the small finger, and so on. And people used to count using the fingers. So even in nowadays, whenever you just calculate how many times, how many points are there while doing a viva, you just count that 1 2 3 4 using your hands, that I have 5 points. So while telling the first point, I just open one of my fingers. While telling the second problem, the second point, I am just opening my second finger, and so on. We just count it using the fingers. So now in ancient time people had, not ancient time actually, but even in current days actually, it is true that people have um, 20 fingers, including the fingers from the hands, two hands, and the two legs. So in ancient time, people used to say that we can count only up to 21, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now, or maybe 20. So let me write it down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So let me draw the fingers then. The small finger, the ring finger, the middle finger, the index finger, the forefinger. Okay, here is another sets. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and there are also 5. 1, 2, 3, 4, 5. 5 toes. 1, 2, 3, 4, 5. 5 toes. And then 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Now suppose I have given an ancient man 21 bananas. So how will it count? He will count like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and the 21 will round up here again. Right? He will count the 21st banana using his the small finger. So that means you are representing this one, you were representing 21 by this one. You are just representing. Though this one was only assigned for the first count, but you are also assigning the 21 to this finger only. Okay. So you can always see that here is also a quotienting. Now 21 is being quotiented by 20. That means that remainder, that is 1, that will just run back to first element. And that is the very notion of quotienting. In some world, in their world, suppose there are 21 bananas and someone was in the cave and he just came out of the cave and said the counting man is holding his this small finger as the last counted finger of the 21st bananas. What would he say? What would he think? He cannot perceive that whether there is one banana or 21 banana or 41 banana or 61 banana, right? Because he only sees that the last counted number is 1 itself. So in some sense the 21 are 1, 21 and 1, 1, 21, 41, 61, all these numbers are same in some sense, because those are all being represented by the single unique finger. So this is the notion of remaindering. That is, in we say it is in mod 20 world, 1 and 21 is same, so is 41. But in reality 1 and 20 are not, 21 are not the same. It is evident because suppose someone gives you 1 rupee, or someone gives you 1 bucks, or 1 buck, or someone gives you 21 bucks. So that is quietly, I mean, you will more happy if you get 21 bucks. So 1 and 21 are not same, but in mod 20 world both of them are just the same. So this is the philosophical idea of remaindering. So now, as we said in the very first portion of the lecture, that congruence means something similarity. Congruent triangles mean there is a similar triangle. That is a, if I take a triangle and if I have two congruent triangles, if we take one of them and paste it on another, they will exactly merge. The similar, they are exactly similar. So in this sense, the congruence means in mod 20 world 1 and 21 are exactly same. That is, they are congruent. Now let me formally define what a congruence is. A congruence, that means let n be a fixed positive integer two integers two integers or maybe a comma b integers are said to be congruent to each other modulo n symbolized by a is congruent to b mod n. Sometimes we write like a congruent to b mod n. Sometimes we write it as a equal to b, though this is an abuse of notation, but sometimes people write like that. If n divides a minus b, this is a symbol that means divides. Okay, that means 2 divides 10 but 3 does not divide 10. This is a straight vertical bar. That's it. So this means what? That is, a minus b is equal to kn for some k in z. This is the most important thing. Now there are some examples. Take mod 7. That means mod 7, as we said that let n be a fixed positive integer. So we are fixing a positive integer. N is equal to 7. In mod 7 world, look very closely that 1 is congruent to 8 mod 7, 0 is congruent to 7 mod 7, minus 1 is congruent to 6 mod 7, minus 2 is congruent to 5 mod 7, minus 3 is congruent to 4 mod 7, minus 4 is congruent to 3 mod 7, minus 5 is congruent to 2 mod 7, and minus 6 is congruent to 1 mod 7. Similarly, minus 7 is congruent to 0 mod 7. So I hope this is clear. If not, then try to figure out using this definition. You can always find that 1 minus 8 or 1 minus 8 is divisible by 7. That is equal to 1 minus 8 is equal to minus 7, and minus 7 can be written as minus 1 into 7. So minus 12 is congruent to 2, again mod 7. 82 is congruent to 5 mod 7. 91 is congruent to 0 mod 7. 11 is congruent to 4 mod 7, and so on. You can find it out by yourself. Another example, or maybe you can say that a note observation, maybe note that if A congruent to B mod n, then what can we write? By definition, A minus B is equal to some nk, that is equal to A is equal to nk plus B. That means, so whenever I have this A, I can write it as some nk plus B. That means A congruent to B implies that if I divide A by n, I will get a remainder that is equal to B. Now, here is a little confusion I can uh, comprehend, that everyone is thinking that in this case 1 is divisible by 7, I will get 8 as remainder, but in division algorithm I got remainder must be less than 7. So there are certain properties of this congruence that we will discuss later, and from there you can see that it is not at all a confusing matter, but it is in harmony with what we have already defined. Okay, so we proceed on by stating a proposition. By stating a proposition, and what the proposition is: for arbitrary A and B, A congruent to B mod n, if and only if A and B leave the same remainder when divided by n. So first we prove the only if part. Proof: the only if the only if part can also be written as like this: the only if part, that means A congruent to B modulo n, then A and B will leave the same remainder when divided by n. Suppose we prove it by contradiction. Suppose not. Suppose not. Then what will happen? A is congruent to, well, when A is divided by n, it leaves a remainder k1, that is n into q1 plus r1, maybe r1 not k1, that is r1 is less than a and is greater than or equal to 0. And suppose not, then it will happen and B is equal to NQ2 plus R2, and this R2 is also less than A less than B. Now what will happen, that A minus B is equal to N into Q1 minus Q2 plus R1 minus R2. But from here, let this be star. From star we know what? A congruent to B means, modulo N means A minus B is a multiple of K. So now comparing this double star with star, these two results comparing, we get what? That Nk is equal to N Q1 minus Q2 plus R1 minus R2. Now simply think, if R1 is greater than R2, then R1 minus R2 is greater than 0, and both of them are actually, and R1 comma R2 both are actually less than N. Now think very delicately. N K minus Q1 minus Q2 is equal to R1 minus R2. Clearly, N is a positive number and R1 minus R2 is a positive number. So K1 minus Q1 minus Q2, this has to be a positive number, right? But that will imply that K minus Q1 minus Q2 is greater than 0. This is done. Now think that if I talking about, let this be L. Now L is a number which is greater than 0, and all these numbers K, Q1, Q2 all are integers. So we can think like L is an integer, right? L can never be a fraction. So whenever I will multiply this L with N, I will get a number which is greater than or equal to N. And I am here getting NL is equal to R1 minus R2, which is greater than or equal to N. But if R1 and R2 both are less than N, and I am taking R1 minus R2, that must be less than N. That is a contradiction, right? Because if R1 is less than R2 is greater than R2, both are less than N, then 0 is less than R1 minus R2 minus N minus R1, R2, that is strictly less than N. This is a contradiction. So I get this. The similar argument will follow if R2 is greater than R1, then we just simply write it as R2 minus R1 is equal to N into Q1 minus Q2 minus K. And the whole argument will follow in the same direction. And that way we will again get a contradiction, and that contradiction will say that R1 is must be equal to R2. R1 is equal to R2. Then we are done for the first part. Now if part. That means if they leave the same remainder, then they are congruent. This is quite trivial. That means suppose A is equal to n q1 plus r1 and B is equal to n q2 plus r1, then what can we say? That A minus B is equal to n q1 minus q2, and that implies that n divides A minus B, and that will imply A is congruent to B modulo n by the definition. And hence we have proved that two arbitrary numbers are congruent modulo n. That means they leave the same remainder when divided by n. So now it is just a matter of manipulation that you can actually see that all these statements, the division algorithm, the size of the remainder, and this note or this observation and this observation, as we discussed just a bit ago, are all in harmony by just garlanded by this proposition. And hence we can think like a congruence is just like the set of all remainders. So we will talk about that a bit later. You need to be a bit matured on this field of congruence. Maybe one or two lectures maturity will be enough. So we will discuss that thing in our next lecture. So till then, well, adios.